Welcome to qnawire.
All right, in this problem, we were asked to look at the ideal gas law and the van der Waals equation of state for a scuba tank. So this is a four-part problem. I've showed the first three parts. In part A, we're asked if 2,300 liters of air are brought into a tank that's only 12 liters large at a pressure of initially at a pressure of 1 atmosphere, and the temperature is 20 degrees Celsius. And throughout the process, show that the amount of moles in the tank is going to be 96 mole. We can do that with the ideal gas law pretty simply. Part B then asks to use the ideal gas law where we know the number of moles in the tank and its temperature to predict pressure. In part C, we're asked to use the van der Waals equation to predict a pressure in the tank, where we assume some values, the parameters for air of A is 0.1373 and B is 3.72 times 10 to the negative 5. And finally, in part D, we're asked to confirm that the percent error is about 3% between these two. So let's start us off. For part A, we're asked to use the ideal gas law, which is PV equals nRT, where R is the gas constant, N number of moles, P is pressure, V is volume, and T is temperature. We know all these things except for N, which we are asked to confirm. So N would just be PV over RT. Pressure in pascals is about 1 times 10 to the 5. We're given the volume of, which ends up being 2.3 meters cubed. Gas constant's always 8.314, and its units are joules per mole Kelvin. And our temperature, which is 20 degrees, is 293 Kelvin. Remember, we have to convert to Kelvin and pascals to keep our units consistent. We are left with 95.64 mole, which is approximately 96 moles, which is what we were asked to confirm. So that's it. So that's not so bad. For part B, we once again use the ideal gas law, except now we need to find pressure. So PV equals nRT. We're given the number of moles in the tank in this case, and the temperature, and the volume of the tank. So pressure is just going to be, let's put it over there. So pressure is just nRT over V. So we have to convert these volumes to meters cubed. So the volume of the tank in meters cubed is 0.012. Number of moles we assume is 96, because that's given in part B. Once again, the gas constant 8.314, and a temperature of 293 Kelvin, or 20 degrees. All right. And we end up with about 1.9 times 10 to the 7 Pascal. Cool. Which is about 190 atmospheres, because remember, 1 atmosphere is about 10 to the 5 Pascal. Cool. So you can see that this air in the tank is quite pressurized. It's almost 200 times the pressure of the regular air. All right, so I'm going to go to another page for van der Waals equation because it's usually pretty large. Let's do that. All right. So remember the van der Waals equation, P, the predicted pressure for the van der Waals equation is RT over V over N minus A minus B. Always mess that up. And then it has a second term minus A over V over N squared. Great. And so we can expand this a little bit to make it a little bit easier to calculate things. This is equivalent to nRT over V minus NB minus AN squared over V squared. Okay, so we're going to use the exact same values as in part B for the volume. So I'll just write that out. If volume is 0.012 meters cubed, temperature is 293 as before, Kelvin. And we have our values A and B from before. What was A? It was, right, it was 0.1373. And I'm just going to take the units off because they're kind of messy. And B is 3.72 times 10 to the negative 5. We could put all these values in and compute P, which comes out to be about 1.9 times 10 to the 7 Pascal. All right, so far so good. Cool. So finally, our last part is all we have to do is compare these two values. And because they're so close to each other, we actually have to use more precise values to get this percent error. I've just included the approximation to like 1 or 2 significant figures. But we have to do a little bit better than that. And I'll include the more precise values here. So we have our pressure from the ideal gas law minus the pressure from the van der Waals equation, or the pressure from the van der Waals equation. We're just getting a percent error here. So we're just comparing the pressure from part C and the pressure from part B. All right, so now I'm going to quote you some more precise values of these so we can actually get a good percent error. So we have 1.9488 times 10 to the 7 Pascal. That's the ideal gas law. And 1.8958 times 10 to the 7. So I just listed these as 1.9 each in part B and C, and that's sufficient. But now we have to be a little bit more precise. Okay. And once we calculate this, we end up with 2.796%, which is approximately 3%, which is what we were asked to do. And that's it. We've confirmed it. So the van der Waals equation and the ideal gas law both give you pretty close estimates for pressure inside a scuba tank. They're slightly off, but pretty consistent with each other. So that's it. Just practicing using those two equations of state for the gas.